All right. Recording started. Go ahead.
Oh, you started? Okay, hold on. Hold on, my computer. Hold on, give me a second. Quick down. Oh,
Technical
now that's
jitters.
okay. Yeah, hi everyone. Welcome to the new one word series. Today we have honor to have Dr. Pratik Patel to give a talk on his recent research revisiting model complexity in the wave of parameterized per over
Parameterized. Yeah, it's a hard
parameterized
word. Yeah, I know.
machine. A little bit
I also
background
have
for
trouble saying it.
yeah.
Yeah.
Pratik.
Okay.
So no, give you some
Oh,
background.
sure, sure. Okay.
Pratik is currently a postdoc fellow in the Department of Statistics at UC-Berkeley under the guidance with Ryan Tipshani. She he get her PhD from CMU, and then before that from statistics also and the computer engineering. Before that, he got his bachelor from University of Toronto and pursuing like a engineering, like a electrical and communication engineering. So he had very unique and very strong engineering background and also very strong writer background. So now take the floor, Patrick.
Great.
Patrick,
Yeah.
yeah.
Thanks, Yang. Hi, everyone. My name is Pratik. As Yang said, I'm currently a postdoc at Berkeley, and I'm going to be talking about work on model complexity, especially in the context of overparameterized learning. Yeah, it's a hard word. Well, I'll explain what overparameterized is. Some of you may have heard of it. Okay, so this is joint work with Jin Hong, who's a student at CMU, and Ryan Tipshani, who's also my advisor. There's a link to the paper on which this talk is based on. It says you go to a tiny URL, model complexity. That's the paper. We recently put it out, so we'll love to have your feedback on it. Okay, to set the stage, some of you may already be familiar with this, but let me just, for the completeness, say a few words about this. So the talk will be focusing on overparameterized learning. And so overparameterized here means there is more parameters than the number of observations, or at least like proportional. And as we know, the machine learning model these days fit a large number of parameters. And by parameters here, we can either mean the raw features in the data set or learned features. And so the overparameterization seems to be useful for a number of things. One is that it allows you to represent rich and expressive model classes. Somewhat surprisingly, if you have an overparameterized model, optimization problem to fit such models somewhat simplifies in the overparameterized regime. So even like simple local optimization methods somehow like find near optimal solutions sometimes. And even more surprisingly, seems that without any explicit regularization, models seem to perform well on unseen data, even if you have lots of parameters. So the entire talk is going to be about this third aspect, about the generalization or like performance out of sample in this overparameterized regime when you have way more parameters than number of observations. Okay, and just if you have any questions within the talk, just ping me. I'll try to monitor the chat, but yeah, you can just sort of unmute yourself and ping me. Okay, so I guess I'm sure everyone here is familiar with this curve. It's called the double or multiple descent, but for to pay homage to the literature, I'll briefly recap here. And so the talk is mostly going to be sort of circling around this. So this is a plot from an influential paper by a bunch of folks, Belking, Su, Ma, and Mondal. They looked at various model classes and their generalization, or their out-of-sample performance, their error, out of sample, as you increase the capacity of the model. And so the model here, that class could be anything. It could be neural network, random forest, and so on and so forth. And the capacity here would be sort of either the number of parameters or some sort of like notion like that. You're increasing either the number of trees, the number of parameters in the neural network, and so on and so forth. And what they observed was that the prediction risk curve, so this is the curve, as you increase the capacity, initially follows this sort of U curve. That's sort of the classical understanding of your like generalization, roughly in terms of bias variance trade-off. And so they observed that up to the point of so-called interpolation, where your model is rich enough that it can fit to the data completely, you sort of have this U curve behavior. But if you try to sort of increase the capacity even beyond that, so you add more and more parameters, so you're already sort of completely fitted to the data, but you're trying to add even more parameters, that the error again decreases. And so this is the so-called modern interpolating regime. And so this phenomenon is just double descent. And so the double descent here basically is just that there's first descent here, that's the classical descent. And then there is this another descent, that's the double, that's the modern descent. And so they observed this for empirically for many different model classes, linear regression, where you add more number of sort of variables, kernel regression, random forest, you add more trees, boosting, you sort of allow for more number of iterations, neural networks, you have add more parameters and so on and so forth. Okay, so I guess the talk is mainly going to be focusing on sort of this double descent behavior. So it's a curious sort of phenomenon. And somehow the thing that we'll be focusing on this is x-axis. So when you plot this kind of curve, you sort of plot some sort of simplistic notion of capacity. So you sort of just count the parameters or the iterations, number of trees, and so on and so forth. And so what we really want to sort of understand is that, is there a parameterization of this x-axis where instead of looking at sort of the raw notion of complexity, you try to reparameterize it so that this doesn't seem like too much of a surprise. Okay? So that's sort of the overarching goal here. Okay, but before that, let me just say that when this paper came out, this was kind of like sort of an interesting take on this overparameterized models, and so this was empirical. So people sort of in the last 5 years have been trying to understand this sort of behavior more theoretically, and there's lots of work on this. So there's linear regression. People have sort of precise understanding of that curve, kernel regression, various local methods, and many more. And so this is already like sort of out of date. But so let me sort of give you sort of like what's the current understanding of all of this. So in a nutshell, as I said, that the current practice is that you have your models which have way more parameters than observations. You typically do not keep it under regularized. Don't regularize it too much and just run whatever first order method. So let's say stochastic gradient descent, and you just fit. You train and train and train. The models eventually may interpolate or is near interpolation. So achieve zero training error, and you sort of still train, and they still sort of generalize well. Okay, and so people. So as I said, that people have sort of some theoretical understanding of that. And there's two sort of nice monographs that if you're interested in this sort of area, one by Peter Bartlett, Andrea Montanari, and Sasha Rocklin, and then one by Misha Belkin. That sort of summarizes all the sort of work I mentioned before. Okay, so now what is the talk about? So we are not going to be looking at that. So we are not going to prove any new results on generalization. The talk sort of it's on an adjacent topic. As I said, we want to sort of understand the notion of the x-axis, the model complexity. And so the questions for us for this sort of paper were, like, is there a good measure of model complexity where the double descent curve doesn't seem like too much of a surprise? And more specifically, I guess we kind of want to compare different interpolators and how complex is like the one interpolator compared to the another interpolator. And so both of them are fitting perfectly to the data. They have different out of sample performance, but in terms of complexity, which one is more complex? And so if you go by the previous plot, like if you just compare the number of parameters, they may not be the right sort of way to compare them. And so sort of we are going to sort of try to understand that in this paper. So, okay, so let me just maybe before I tell you how to do that, I'll just give you the takeaway of what sort of paper does. So we propose a notion of model complexity that's algorithm specific. and applies for any prediction procedure. So you give me your favorite procedure, and you're fitting that procedure on the data, you get some predictor, and I'm gonna, whatever the procedure is that we're gonna give you, will spit out a number. That number is gonna be between 0 and n. So we'll construct it so that it's always between, it's always less than the number of observations. And somehow think that like, if it's n, it's the most complex and 0 is the least complex. And so we're always gonna keep it in this range. We'll propose sort of a family of measures, but the two extremes of those are what we call emergent and intrinsic. And emergent is the notion that will sort of capture the entire complexity, and it's like how well your procedure adapts to the entire response. And the intrinsic is more how it adapts to pure noise. And so the emergent is like if you fit your procedure on like actual data with actual response, that's going to be your emergent degrees of freedom. The intrinsic would be you take your features, but you don't train on the response, and you just fit on, say, pure noise, and that would be more like an intrinsic notion. And sort of this should remind you of sort of Rademacher complexity. So I may draw a connection later, but okay, so these are sort of the two extremes, but we have the entire sort of like the spectrum of things that you could do in between, but these are on the extremes. And roughly speaking, I guess what is the use of all of this is that, I guess, as I said, we wanted to compare interpolators. So you can apply to a bunch of interpolators. So these are sort of the most canonical examples, which is the minimum L2 norm interpolator, minimum L1 norm interpolator. And so these are the ones where you fit completely to the data. So these are linear predictors. And either you keep the minimum, the L2 norm of the estimator small or the L1 norm small. So I'll get into this later, but these are just two types of interpolators. So what we typically observe is that for the interpolators, exactly near the point of interpolation, where roughly on your data, when n is nearly p, this notion of whatever we're going to propose will be maximized. That's like somehow the most complex. But on either side of that threshold, the complexity is small. And so I guess if you now think back to the double descent curve, what roughly that means is that, so on the left, you had this U curve. So that's okay. And on the right-hand side, it's again has a smaller complexity. And so you can basically sort of think of reparameterizing everything that was after the point of interpolation into an equivalent under-parameterized problem. So I guess the way to think about the double descent in this context of like what you're going to propose is that the left part in the under-parameterized regime, when you are below the interpolation, you keep things as were, roughly speaking. But when you're in the over-parameterized regime, so what sort of this will do is that this will sort of try to reparameterize that over-parameterized axis into an under-parameterized axis. Okay, and what is this all based on? So this is based on this optimism theory from statistics and degrees of freedom. Okay, so that's roughly the entire summary. So if you sort of have to go somewhere, you can maybe take a pause here. But okay, let me maybe just stop here to see if there's any questions. But of course, I'm going to explain all that, but just so that at least it's clear where we're going. Oh, there is something in the chat. Let me check. Okay, maybe you can just unmute and say if it's easier. Good question. So the question is that if the interpolation threshold is approximately n, why kept the model complexity at n? Doesn't that limit the analysis to the classical regime? No. So I guess good question first. So what procedures we're going to apply? That's not the restriction. So you're going to apply to both the under-parameters and over-parameterized. The restriction here is more like it's a feature of the whatever we're going to propose, is that you'll spit out an answer which will always be between 0 and n. And so this is just a choice, right? I mean, in some sense, you are designing some sort of a unit. And so we are saying that in that unit, the maximum unit is n. and the minimum unit is 0 somehow. And so you'll kind of see that why sort of we prefer to have between 0 and n. But this is not a restriction on the procedure. The original procedure can be like, of course, we're going to also give a measure for things in the overparameterization as well. It's just that the most complex model will have somehow n model complexity. And so we're going to do it in terms of degrees of freedom, so you'll see. But you somehow think of this as the most saturated model. And this is like the most simple model. Okay, does that clarify? But I mean, it will become clear when I explain also, but. Okay. All right, so maybe let's move on. Okay, so I guess before I go into the actual how we do this, I guess let me just take two interludes here. So one is I've been saying this interpolators, but you may ask, and so reasonably so, is that like, why do we actually care about interpolators? I mean, it's fine that the neural networks practice is training models to completely fit the data, but maybe like, but why do I care about it? I mean, apart from that, the neural networks sort of example. And actually, there is a good reason that we should care about it, is that even in a very simple model class, like just a linear class, let's say you're fitting least squares or ridge regression, like this sort of phenomenon of interpolation is interesting. And this is somehow, I think that at least the statistics community has not paid much attention to, and I think it's sort of something that we should all sort of pay attention to, is that suppose you're trying to fit ridge regression on a very simple like linear model. So I can write down for you a linear model, and I'm saying you have this ridge regression. Of course, it's a high dimension problem, and you're trying to find the best tuning parameter lambda for ridge regression. And it can turn out that even if I had my data generated from like linear model, that and the realistic sort of features, just like Gaussian features, that the optimal lambda could be 0. And when the optimal lambda is 0, and in the case when you have more parameters, basically that becomes a minimum L2 norm interpolator. So you have this ridge regression if you send the parameter to 0. And if you're in the underparameterized regime, this is the least squares. But if you're in the overparameterized regime, this will completely fit with the data and will interpolate. And turns out that there are sort of very simple examples you can do where the sending lambda to 0 could actually be optimal in high dimension problem. And this was pointed out by a very nice work empirically about in 2020 by Kopak, Lomond, and Sanchez. And this was actually a stack exchange stacking exchange sort of post where they just found this sort of, they were playing around with some data sets, actual data sets in sort of genomics. And it was overparameterized data set, so the P was larger than N. And they're just trying to like train ridge regression. And so they had sort of different number of features. So the data set had something maybe 1,000 features. And they're just trying like, okay, so if I don't have 50 features, I'm trying to tune the ridge regression and see what the optimal lambda is. You get some value. And so they keep adding more and more features. So the data set maybe has 1,000 features. And they saw that like as you increase the number of features, the optimal lambda is very small. And so this was the double descent curve we just saw before. That was for lambda 0. And so you may say, well, okay, fine, that it has this behavior, but why do I care about that? Because I'm always going to tune the lambda in ridge regression. But it turns out that like the actual, if you tune lambda, it can actually be, the optimal lambda can actually be 0. So this point here, this at some value of P in here, the optimal ridge regression could just be minimum L2 norm interpolator. And it actually can also be negative, which is also sort of interesting. Yeah, so it's not a pathological example somehow. So the interpolators are of course interesting in practice as well, that you can, if you have a problem, it's a high dimension problem, that the interpolator could actually just be optimal. Okay, and so that's a one interlude. I guess the second interlude here is that, well, okay, you may ask, well, okay, so fine. Let's not worry about the model complexity for now. We know interpolators can be optimal. How does that, like in practice, do I have to worry about this? Like suppose in practice, I'm tuning this lambda using some cross-validation, right? So either I'm doing split cross-validation or leave one out or things like that. And does cross-validation even work in this regime? Okay, so the short answer is that for each regression, yes. And so this is, I'm sort of giving some sort of pointer to previous work where we show that for rich regression, CV, and so either leave one out CV or generalized cross-validation, both are uniformly consistent over the tuning parameters that also include 0 and negative values. And so in particular here, so if you're trying a problem where you have, let's say 2500, so 2500 sort of n, and then p you vary from like 100, 2000, 5000. So 5000 will be the overparameterized regime, and then these two are underparameterized. That even though your training error, so in the red here, you're sort of plotting the histogram of the training residuals. And so the interpolator has everything is completely fitted, so the residuals are completely 0. So of course, the training errors are not tracking your test errors, but if you did GCV or leave one out, if you sort of take those residuals, you correct them using, I'll show how, but somehow the takeaway is that you can actually just estimate even the entire distribution of the out of sample error. And so the upshot is that CV works. And roughly speaking, and so I think this is sort of a beautiful cancellation here for CV. So let me just sort of tell you that as well. And so roughly we call that for leave one out cross-validation. What you do is you take your data, you leave one guy out, and you fit your estimators and you estimate on the thing that you left out. And for each regression, there is this nice shortcut. This is called the so-called shortcut formula, where you don't have to refit n times. You just have to fit model once, and you can sort of take your residuals and divide by some sort of number. This is the hat matrix, and 1 minus the diagonals of the hat matrix. So there's some shortcut formula without having to refit everything. And what happens is that in the overparameterized regime, when you start trying to send lambda to 0, it's an interpolator. So you'll have your residuals completely 0. And turns out that even the denominator is 0. So you're in sort of a 0 by 0 form. But there is a beautiful cancellation that happens here in terms of sending lambda to 0, that you can still get a shortcut formula, which is sort of a limit of this formula. And what we show in the previous work is that this formula works. So that if you are tuning in practice and suppose interpolator is optimal in overparameterized regime, you can still use like the shortcut formula, a version of it, and that will work. And so there is a similar sort of approximation here, where instead of diagonals, you take the trace in terms of the generalized cross-validation. That also works. Okay, so that was just an interlude to sort of like minor points. Okay, so I guess now I'm going to move on to the details on sort of how we do the model complexity part. And all of this is going to be based on the notion of degrees of freedom. And so I'll try to first explain the degrees of freedom. What does that mean? And what is sort of the statistical, what is known in statistics before, and then what our contribution is. Okay, so degrees of freedom. So what does it mean? So you probably have heard of this word, and this is sort of a word that gets used a lot. It means different things to different people, but there's sort of a core idea behind it. And what the core idea is trying to say is that like it's some sort of effective number of parameters of something. Okay, so it's some effective number counting. So in general, if you have sort of a mechanical system, then it's the sort of that something could be mechanical system, and physics and chemistry could be a physical system, and the statistics, something is the procedure. And in each case, that the degrees of freedom is going to count some sort of independent axis. And usually you can sort of try to guess the effective number of parameters in sort of this system. So that's sort of like, at least qualitatively. If something is like has more degrees of freedom, means that it has more freedom. It's a more independent components. Okay, now more specifically in statistics, traditionally is sort of degrees of freedom are defined as the effective number of parameters used by the procedure. Okay, so this seems vague, and so what does it mean? Right? This is used by the procedure. So we'll shortly see the precise definition. But before that, so what is it useful for? And so why would you like want to like define this notion of degrees of freedom? So typically the way people think about this is that it sort of gives you a way to put different things on the same footing. And so what I mean by that is that, so if I have two procedures, procedure A, procedure B, and you may have done, like they may have different sort of hyperparameters and so on and so forth. And I sort of want to know like how much each procedure is spending somehow, how much sort of, like how many parameters is it spending. So it may be, one procedure may be like better at prediction, but it may be spending more somehow. And somehow you kind of want to sort of qualitatively understand, if I give you some X number of sort of budget, and so budget is a bit vague, but I sort of fix some sort of degrees of freedom, which one is a better procedure? And that's roughly, traditionally at least, how people think of the use of degrees of freedom. That is one use. It gives you equal footing to compare different procedures. Okay, so but I have not told you what that is, so let's just go and define it. So it's in statistics is a sort of a classical topic, and goes back to the work of, like you may have heard of Mallow CP. Stein has a work on estimating the mean of multivariate random variable, so normal, where sort of he mentions, he comes up with the Stein's formula. Efron has a lot of work on it. And so what is it? So let's say you have an estimator or a predictor, f hat, that's trying to estimate a regression function f. So that's it's trying to sort of get an idea of the regression function. And I have sort of n training points. So we define the degrees of freedom of the fitted predictor f hat as, so you take your f hat, so f hat you evaluate on, you have n training points, you evaluate on each training point, and then you take the covariance between whatever is your response at that particular observation and this fitted value. Okay, you sum over all the data points and you divide by the noise level. So noise level is sort of the second moment of your conditional distribution. And what this is roughly trying to capture is that, suppose I have high covariance between f hat and y, means that my predictor is sort of overfitted somehow. Like it is trying to just, it's exactly like yi. So a higher degrees of freedom means that there is sort of a higher sort of correlation, and somehow it's higher degrees of freedom. And the key fact here is that if you, and the reason why people sort of like this notion is that if you take a least squares, right, so you're fitting least squares on p linearly independent columns, and so this would put it in under parameterized regime, because that's where you have these independent columns. And if you evaluate this covariance formula, then you're going to get the answer to be p. And roughly sort of that makes sense when you think of like linear regression in an under parameterized regime. So your data has n things, p is the number of columns, and it's a tall matrix. And you think of, okay, how many parameters am I using? And roughly, like if I have p columns in the under parameterized regime, I'm using p number of sort of my degrees of freedoms are p. I'm using p parameters. And I mean, this seems intuitive. The sort of the part that I find is quite interesting here is that like this sort of holds no matter what x is. So you do not need to assume anything on x and anything on y. So I think, I mean, it's intuitive, but it's also quite powerful that like for any x and y for least squares, if you sort of evaluate this covariance formula, you will get p as the number of that's the degrees of freedom. Okay, so now you may ask, okay, so this is great. So you have some notion here of degrees of freedom, and is that all? Like, so why don't I just sort of take this as my measure and then declare this as the model complexity? And so somehow the key issue is that this notion, when it was defined, is sort of tied to what is called fixed X setting. And what I mean by fixed X setting is that it's you think of all your design matrix as sort of it's a design, and all the X's are fixed. And so okay, so maybe it's better to tell you where the formula is coming from, and so that may make more sense. So what you do is you have this prediction procedure F hat, and you think of the xi's, that those are your data, the observations in your data set, and you think of those are fixed, and you think of just predicting at those x's. And so y are the things you observe. You train your F hat on those, and you think of trying to predict on the same axis. So yi star here is another draw from the conditional distribution at that fixed x. So you're fixing x, you draw another y, and you say, well, okay, that's what I want to I want to somehow predict at that xi, and I'm going to sort of declare my error as like the difference between my F hat at that xi and then a new draw at that xi. And so in statistics, this is called the fixed X prediction error, which is the error on those x's. So note that this is different from training error. So the training error is this one, where you're comparing your yi to F hat. Y is the one that you use to train F hat. This one is still a prediction error because the yi star is a different draw, but it's at the same x. And so if you're in machine learning, this may seem a bit weird because in machine learning, you typically have a new draw, and so you don't compare error on the same axis. And so that's why so there's a sort of a distinction, but this one is fixed x. But in any case, you sort of try to look at this error and you sort of do some sort of calculation. You'll see that what comes out as the remainder term is exactly this covariance term. And then you define your DF to be in sort of the term that will make that formula true. And so that's where the covariance formula is coming from. And in statistics, the difference between these two things, so this is your training error and this is your fixed X prediction error, is called the optimism. If you're coming from machine learning, you may recognize this more as a generalization error or generalization gap. But note this is in the fixed X setting. So this is for the same axis. Okay, so I guess you can see in here that that's sort of one reason why in statistics people have been interested in this DF is because if I have some estimate of this DF, then if I have some training error, and if I add this term 2 sigma square by n times some estimate of DF, then I'm going to get some estimator for my fixed X prediction error. So that's why in statistics, classically, people have been interested in this object. Oh, there's a question. Let me see. Have you assumed that does not depend on X? Yeah, great question. Yes. So for the talk, yes. We are just assuming that here, the variance does not depend on the conditional variance. It does not depend on X. But this can be extended to case where this does depend on X. But for simplicity, for now, let's say that. But in the paper also, I think we assume for simplicity. But the theory that we're going to sort of do, that's an orthogonal part. Like you can extend to the case where this can depend on X. That's okay. Okay. Any other questions? Okay, maybe I should just continue. Okay, but so yeah, so this is why, as I said, in statistics, people have been interested in this sort of object, the degrees of freedom. Now, but this also kind of tells you that I'll be sort of stressing this point of fixed X, is that this is also a shortcoming because fixed X setting is not somehow, I mean, it's interesting in some applications. If you're doing some sort of experiment and your design is fixed, in like say agriculture or something, it does make sense to look at this sort of error. But in machine learning, you typically don't think of this fixed X error you think of an error where your new point is a new draw from your training your feature distribution. So what you really want to do is you want to sort of get good at predicting on the new point, and you're going to compare the f hat at new point with a new response. And so this one we're going to call now the random X error, where it's the X you're going to draw is a random draw. It's not the same X that you use in the training. And so this is the random X error. And so somehow this is going to be so I guess just to give you like where we're going is that we're going to kind of try to extend this definition of the degrees of freedom, which is sort of done in the fixed X setting, with the random X setting. But before I do that, let me just kind of like say, are they different? So there's some fixed X error here. And so now I'm saying there's a random X error here. So how different are they? Now, classically, the reason why I guess people were kind of okay with this fixed X error is that the fixed X error and the random X error for some class of problems are not too different. And in fact, the entire empirical process theory is kind of tries to give you bounds between the fixed X error and the random X error in terms of some sort of function class. So if you're fitting your f hat, and if you're doing some ERM or something over some function class, then the difference between the two you can bound by some notion of like sort of dimension of the class. So in sort of rough heuristic you should keep in mind is that for smooth problems, either where your f hat and f are both smooth or you're in low dimensions, the two things are not too different. And so these two errors would not be that different. But what happens is that if you're in a high dimensional regime, and in particular overparameterized regime, or you have non-smooth either f or f hat, then these two objects can be very different. And especially this happens for interpolators that generalize. Okay, so what happens? For interpolators that generalize, your random X error is going to 0 because it's an interpolator is generalizing well, and it's keeping it either 0 or small. It's keeping its excess random X error small, but its fixed X prediction error, it's pinned at the noise level. And so why is that? It's because it's always predicting on your Xi's, always predicting Yi. So if I'm drawing a new Y, which is Yi star at that Yi, then you can just do rough calculation and see that like this is always going to be at the noise level, meaning that the conditional variance of Yi. Okay, so there's a huge difference. So your noise level could be high, and so these two are quite different. And in fact, for any interpolator where you're perfectly predicting at the input points, your DF, you can just do the calculation using covariance, which is covariance of Yi with f hat of Xi, which is also Yi. It's perfectly correlated at every point. And then you're going to, if you sum over all of this, you're going to get n. So n sigma square. So and then do sigma square. So you get the whole, once you normalize by sigma square, n. And so and this is useless because for any interpolator, this will tell you that the fixed X degrees of freedom is n. And so that's not useful because you want to compare between different interpolators, and so this will not sort of be helpful to compare them. And so that's basically sort of the main motivation for us is that we like the idea of degrees of freedom, and that seems like a useful notion, but we cannot rely on the existing notion of degrees of freedom that's good for a fixed X setting, and I mean that's motivated by fixed X setting. And so what we are basically going to do is that kind of extend that notion to random X degrees of freedom. Okay, so I guess maybe as an example, yeah, I can maybe just repeat this. So we did this before, is that for linear regression in the underparameterization, I told you can do this calculation, you'll always get P, and P is smaller than N, that makes sense. But if it's in the overparameterized regime, so you have interpolator, you can again do this sort of calculation. You either do it using like Yi or like just rough linear algebra calculation, you're always going to get N. And so this is, as I said, this is not very useful. And this is not useful because I just have to show a picture here that we do know from this sort of, okay, so on the right-hand side, I'm sort of looking at, so this is the reachless or minimum L2 norm interpolator. And I'm in a problem where I have 100 as N, and I'm changing the number of p. And so before p, my degrees of freedom is before n, my degrees of freedom is always p. So it's a line, and so I have some sort of curve. This is my error curve, but after that, it's always pinned at whatever n, so 100. But I do know that my error changes. So I cannot rely on the fixed x for this, and I need sort of new notion here that can distinguish between different errors here. Okay, so I guess the goal now then is we want to generalize df so that it connects to random x error instead of fixed x error. And we kind of want to do it for any predictor, so even for interpolators. So that's like one goal, and so we're going to do that. And I guess moreover, we want to go a bit more and say, well, okay, so we have some sort of this df, and I may have different components. I may want some sort of decomposition of the df according to some sort of components. It could be like bias and so other things that could impact my df. Okay, so now I'm going to try to go to the proposal. The disclaimer is that like the idea is actually pretty natural, but yeah, so it may seem sort of simple, but I think it's a benefit that it's simple. It's a natural idea. Okay, so let's do that. So now stepping back, so okay, we're going to try to like sort of think of a notion of complexity, right? So the way we're going to think of this is that, so what is a complexity? And it's really two things. One is that you need some sort of a metric. And what is a metric? So you have to tell me that like, when is something big and when is something small? That's my metric. And you need to tell me sort of some sort of reference. Okay, so one is our metric, and the reference is something that will help me contextualize this metric to put the units on that metric. Okay, so metric is what, so we're going to basically take our f hat. I'll give you some metric, but the metric, what it'll do is it will assign a number to that f hat. Okay, so you get that number. And then I'm going to give you some reference that would help you put units on that answer. So basically, you're going to get two things, right? So you have your f hat. You'll have some metric. I'll tell you what the metric is. The metric will spit out some number. I'm going to take that number, and then I'm going to have some reference, and I'm going to use that reference to put units on that number. Okay. And what we want is that we want the metric to be somehow, that's just a choice. So you choose the metric to be negatively oriented, meaning that a smaller number in the metric would be a lower complexity, and higher would be more complexity. And the reference we're going to choose to be something that it's a good notion of to put units, and it's something that like it's a reference that we're happy that if you count our number using that unit, then it sort of is reasonable. Okay, so let's do it. So before we jump into the random x directly, so let me sort of use this philosophy of defining complexity to see, can we actually just do fixed x df? So I told you fixed x df is like, people have sort of covariance formula for it. And I'm sort of telling you that like, okay, so we're going to take a step back and look at things from this perspective. Can we at least get the things we already know? So let's first reinterpret the fixed x degrees of freedom using this sort of higher level idea. And actually you can do it. And so the thing that basically helps you do that is, so you need two things, as I said. One is the metric, one is the reference. So the metric is essentially just going to be the fixed x optimism. And we call the optimism was just the difference between the fixed x prediction error and the training error. So that's your metric. And you need the reference, and the reference is just going to be least squares. Okay. So more formally, we will define the fixed x df to be the number k such that if I'm fitting least squares with k number of features, that the optimism of that's the reference optimism, is the same as the optimism of the procedure you're giving me. Okay, so in some sense, like you're giving me f hat, my metric is the fixed x optimism. I'm going to compute this number, and then I'm gonna search in my reference class. So my reference class is least squares with different number of k's, different number of features. I'm gonna search in that class and say, well, what k is this matching? Well, it doesn't need to exactly match. So we're gonna say, find the k so that this optimism exceeds my optimism. Okay, so it's the smallest k for which the optimism of least squares with k features is at least as large as the optimism of the given f hat. Okay, and so okay. I mean, now of course I told you that like, okay, this is how we're going to define it. But you're right to ask, well, does that give you the back answer that I gave you before? So you can do the rough calculation that like it's not too hard to show that like this definition exactly recovers the covariance formula you had from before. And the proof is quite easy because it's like for the least squares, the optimism turns out to be 2 sigma square k over n, and this optimism on the left is something 2 sigma square covariance by n, and so basically this will recover the formula from before. Okay, but the good thing is that like this is the higher level perspective on the formula we had before, and because now you have this higher level perspective, this seems like you can generalize this to other things. Okay, now just to give you a concrete example, like so if I tell you that the fixed x df is 5.3, how should you think about this? Is you should just say what that means is that my procedure, at least for the fixed x setting, is roughly the same as the least squares fitted with 5.3 predictors, 5.3 parameters or 5.3 features. Now, of course, the 5.3 is like you're not going to fit on 5, but it's somewhere between 5 and 6. Yeah. Okay, great. And so basically, like you should think of this as I have this metric opt-f. I'm going to put units on it. This is my ruler. This ruler, the numbers are coming from least squares. And then I get my optimism, and I just put somewhere my optimism somewhere here and say, oh, it's 5.3. Okay, great. Now, once you see it this way, it's pretty natural. Now, if I ask you, I have this definition, this works for fixed x. How do I do for random x? The answer would be easy, right? You'll say, okay, f fixed, just change it to random. That's basically the idea. So in the random x setting, we basically define a notion of this with, when we change f to r. F for fixed, R for random. Okay, so in the random x setting, we have the random x optimism, which is basically the difference between, again, the right is a training error. Now you have basically, instead of the fixed x error on the same xi, yi on the data set, you just change it to x0, y0 without a sample. And so you have now what is called the random x error. And the difference between this random x error and the training error is the random x optimism. And in the machine learning, this is known as the generalization gap, but it's in the random x setting. So it's on a random point. Okay, and what is our reference class? I will just choose the least squares again, because least square seems to be a sort of a more canonical class on the k features. But the slightly subtle point here is that in the random x setting, you have to be a bit careful in when you define the reference class, meaning you have to tell me how I choose my features when I fit least squares. So you have to tell me the law of xi, and you have to tell me the distribution of the conditional distribution. And somehow in the fixed x setting, this did not matter because the optimism, the fixed x optimism of least squares was always 2 sigma square k by n in the underparameterized regime for fixed x. But for random x, this is going to matter. But it's not a too big deal. So how do we choose this? And it turns out that even though it does depend on this law of xi and then the response distribution, it's quite universal. And so you can basically do this calculation. So, okay, so let's just pick something. So you're going to basically use your xi's, your features, to be these are features which are composed of some independent features, zi, modulated by your covariance. And so this is like the sort of a standard way of getting features in sort of random matrix array literature, where you think of this sort of like linear features modulated by covariance. So the zi's are like independent features with some sort of moment bounds, and then you're sort of multiplying that by your covariance matrix sigma half, you're going to get those features. So zi is IID coordinates, 0 mean unit variance, some finite fourth moment, blah, blah, blah. And your yi, your response is just a linear. So you have signal, beta, you take this is the signal part, and the noise is independent of your xi's, and epsilon I has a 0 mean unit variance and it's independent of yi, independent of xi, sorry. And you can basically try to compute the optimism of under this law for xi and this law for yi given xi. And you'll sort of find that this optimism actually does not depend on, so you get some number, okay, fine, it's a function of a bunch of things. But importantly, it's not a function of this sigma half. So this optimism is independent of the feature covariance, sigma. And it basically just depends on your n and p. So it's more or less, I guess, the point I'm trying to make here is that even though the optimism in the randomic setting sort of is still a function of this law, it has sort of a nice universal limit somehow. And this is still a sort of a good canonical model to take as a unit. Okay, so this has a formula, you can compute that. And so basically, I guess the final sort of proposal is then this, which is you're going to take your data, you're going to fit your procedure f hat, you're going to compute your random X optimism. This is my left-hand side. And I'm going to take the optimism of least squares, fit it on k features on this RMT data I just said. And you're just going to basically do the matching equation again. You're going to find the k, the smallest k, so that this random X optimism is higher than the optimism of your procedure. Okay. As I said, the right-hand side has this sort of nice formula. And so when you kind of try to solve for k here, it becomes a quadratic equation and you can solve for it. So there's all sort of nice properties in the paper. It's a unique k less than n and so on and so forth. But the basic idea is that you're going to sort of do some matching and find the k from that. Okay. And why is this called emergent here? So I'm using this word emergent is that when I'm compute the optimism, the random X optimism of my procedure f hat, I'm using the entire data, both the features as well as my response. And so this is capturing somehow both all the properties from my response. So in particular, both bias and variance. On the right-hand side here, for RMT data in the in the linear model case, it somehow only captures the variance. But that's sort of a technical point. But it's mainly emergent because on the left-hand side, you're going to be computing everything on like all the data, even including the response. We will see there is a version where we can sort of also get another sort of instead of fitting on all y, we can do it on noise. So you're going to get some another thing. But anyway, let me show you a plot here now. The random X optimism of the least squares here, I said there's a universal limit, and you can kind of check that it's quite sort of nice. Even if you have 50n, the formula that I just showed you in terms of n and p, that's the formula, and then these are the points where you actually compute the optimism of least squares using the data. They're quite close, even for n50. And so this will define for us this sort of ruler where you have this random X optimism of least squares. And as you can see, I mean, here it's that like it's not really linear, meaning as you're increasing k, it doesn't linearly increase. And so that's sort of the point. And in particular, towards the end, when you're reaching near n, this will shoot off to infinity. And so that's a nice thing because the optimism, if your n, or if your k is near n, is really large. So when you're solving for this equation, you can force a unique k that's smaller than n that can match any optimism on the left-hand side. And so this goes back to the point I made earlier is that it's somehow a nice kind of thing here is that you can keep the matching where you take the k to be between 0 and n, and it can match with any optimism on the left-hand side. So you do not need to go beyond n to search for this k. And so our maximum bound would be n, and the lower is 0. Okay, so now once you have this kind of df, what can you do with it? So here I'm kind of showing you different sort of classes of predictors. So you can take KNN, random forest least squares. You can have this sort of like their raw complexity, which is like maybe the number of neighbors for KNN. number of trees for random forest, number of parameters for least squares. And you can compute the random x degrees of freedom. So you're going to get some sort of numbers. And the good thing is now you can take that number and then you can sort of plot the prediction risk as a function of that number. And I guess you can sort of get some sort of interesting sort of things that you can see here. For example, for random forest, the degrees of freedom are like not really changing as you change the number of trees and so on and so forth. So you can sort of get some sort of interesting behavior as a function of this degrees of freedom. Yeah. Okay. I think so. How do I have 5 minutes more? Like, what's the roughly?
Yeah, sure.
Okay, cool. Yeah, I'm just sort of getting. So okay, so so far I told you the emergent degrees of freedom. That was when you're fitting on the entire response. I told you that like there is another version we could do where it's more like intrinsic, and it's roughly the same idea where on the right hand side is always the reference is the least squares. You're fitting on this like random arbitrary data, but on the left hand side, you are basically instead of training on all your responses, you just simulate pure noise, and you compute your optimism on pure noise, and you still do the same matching. And so what you're going to get is that you're comparing somehow. The right hand side is like the reference. You're comparing variance proxy somehow on the left. To that, and then we're going to call this whatever number you get k here would be sort of the intrinsic notion of complexity. And so you can do the same sort of exercise again, where you take all different procedures and you sort of plot their intrinsic degrees of freedom. And so paper has a bunch of properties that sort of some theoretical properties that says how these two relate. And the rough takeaway is that in general, you'll find that the emergent degree of freedom is always higher than intrinsic degrees of freedom, one. And the second is that the intrinsic degrees of freedom decreases in sort of the thing that as you would expect. So in basically, like if you have higher number of features, a higher number of neighbors, you expect that the intrinsic things should decrease. So it decreases and so on and so forth. So the paper has sort of those kind of properties in terms of the model parameters, but you can get these two things. In general, you don't know how they relate, but for specific classes, you can show a bunch of properties. Okay, let me just maybe say in practice how you're going to compute these numbers. So yeah, basically you need like 2 numbers. As I said, you need the optimism of the procedures. So how are you going to get that, you may ask? So you can either do like cross-validation to compute the random X error, the training error you already have. So you can get the optimism that way for the emergent one. For the intrinsic one, you can just simulate or using pure noise. So you fit your position on pure noise, compute the random X optimism for just pure noise. And the reference you already have. So either you can use the least squares. So you can just do it on just maybe final sample data, or you can use this asymptotic approximation that I said. And what you're going to get if you use the approximation is that you're going to get some sort of formula here. And so if you sort of use the approximation, then the formula at the end is basically this sort of formula where you give me your optimism. This is in psi, and you put it in this formula, and then this will spit out a number. So if this psi is emergent, then I'm going to get emergent degrees of freedom. If psi is intrinsic optimism, then I'm going to get intrinsic degrees of freedom. And as I said before, is that you're going to basically get a unique number between 0 and n that kind of gives you this. And this range, I think, yeah. So this goes back to the question we had above before, is that roughly think of the 0 as the least complex and the n as the most complex if you get the answer, and n is more like a saturated model. Okay, now one last thing, I have maybe a couple of minutes. It's about the decomposition. And so what you can kind of say is that like, so what if I sort of try to subtract the emergent from intrinsic? So you're going to get some number. And we can kind of like think of that number as contribution due to bias, because the emergent one had both bias and variance because it was trained on all your y, and the right answer was only pure noise. So this the difference is sort of a contribution due to bias. And so you can kind of like think of sort of like in the same sort of examples, you can sort of plot the contribution, and then you can sort of see the behavior of the contribution due to bias as a function of different like model parameters. And you can take this at one step further, which is to say, well, what if I had other components, not just bias? Like I could have the covariate shift, or like label shift, and so on and so forth. And so you can kind of generalize this idea. It's a pretty natural sort of way of generalizing it, is that you basically take, so right-hand side is always keep the same, is your reference. And on the left, now you have a bunch of components. And so you basically play the game of like turning stuff on and off. So if you have something like maybe covariate shift, you can say, if you have a covariate shift, what is my optimism? If I don't have, what is that? And then you can sort of use the idea of Shapley values to assign a contribution due to that component. I guess I'm running out of time, so I won't explain too much, but if you have questions, I'm happy to chat. It's also in the paper. And the good thing that will sort of turn out at the end is that because it's sort of, if you do it using Shapley values, that if you add up all these contributions, it will give you the final DF. So in some sense, the emergent DF will be composed of all these components, and you can kind of like write sort of the sum of all those components would be the final emergent degrees of freedom. Okay, so just one last like couple of plots. The same running example that we're looking for KNN, random forest, and least squares. The stuff you can do with all this thing is that like you can basically say, I have this sort of emergent degrees of freedom. That's my final degrees of freedom. And then you have all these components. And so in this example, you have some sort of covariate shift that you can assign different contributions to different components. So there's some intrinsic guy that's like the intrinsic due to noise. Then there is some contribution due to bias and some contribution due to covariate shift. And I guess, I mean, it's interesting here is that, like, for example, you can sort of see things like random forest, the contribution to the DF of covariate shift is typically small. So somehow it's like the least affected by covariate shift. So you can kind of do things like that. Okay, now one last final thing is circling back to the thing that I started off with, this double descent behavior, right? So let's say we are looking at for least squares, and you had this sort of double descent thing. So your n is sort of 100, and if p goes beyond 100, that this had this behavior. Now you can do, as a function of that p, plot our degrees of freedom, so you get some curve. But the nice thing you could do now is that you can now say, well, how does my error curve look like as a function of this new notion of degrees of freedom? And you get this U curve for this underparameterized regime. You again get another U curve for this different regime. And so essentially, like, this is kind of like the point I made at the start is that you're kind of mapping every point in here in the overparameterized regime to an equivalent point in this new axis. And because the new axis is kind of distributed to 0 and n, you're always going to get some point below that n that will give you the same number as here. And so basically, like, I guess, kind of like turning the curve. But yeah. Okay. And that's about my end of the talk. So the high level idea is basically that we have a metric. And so suppose you want to find the complexity, you're going to have a metric, you're going to have a reference classes, and we're going to sort of do this matching game of comparing the metric, which is the sort of optimism, to the optimism of the random, the reference model, and we're going to assign the complexity that way. Okay, and we can decompose it using Shapley values and things like that. Okay, and so everything in the talk was restricted for regression, but you can kind of play this game for beyond regression, so you can do for classification. So that's sort of doable. And beyond that, I feel like you can also do this kind of thing for unsupervised learning, but that's sort of like an open area, and we're kind of thinking of that now. Okay, cool. I think maybe I should stop here, but happy to take any questions at this point.
Great, that's great talk. So any question from the audience? No, okay, yeah, so they have one question there on the chat.
Oh, chat, okay, let's see, great. Okay, are the features ordered in some sense? Great, good. Yeah, so good question. So it actually does not matter because of this universality here. So it turns out that if I am, that's a good question though. Like, it was not like, it's not apparent immediately if like that the order should matter or not. But here, if you try to compute the random X optimism of least squares with k features, it just depends on the k. It doesn't depend on the order in which you're putting things in. Yeah. So it's somehow just a nice property of the canonical class, which is the least squares class under this like RMT. Sorry, under this RMT limit. So in here, if you have n and p, and the stuff only depends on p. It doesn't depend on which p you chose. And it has to do with somehow this guy to be independent of sigma. It doesn't depend on sigma. So there's this like nice universality here. Good question though.